All right, guys, looking at 12.1, we are getting into probability here. So something slightly, well, a lot different than what we've done recently. So getting into probability, we got a lot of vocab stuff. This is your intro to probability section. So there's going to be a lot of vocab, just some basics. Get the words out of the way so we know what we're talking about as we move forward. Talking about a probability experiment, an action trial, right? Flipping a coin, rolling a die, that sort of thing. Possible results are the outcomes. So if you roll a die, you could get a 1, 2, 3, 4, 5, 6. Collection, one or more outcomes is an event. So what you're looking for, right, is, you know, we've talked about in the past, probability of flipping a coin and getting a heads. That getting a heads, that's the event, right? It's what actually has occurred. And then the most important one here, because they're going to ask questions about it, is what is the sample space? And the sample space is all possible outcomes. So your possible outcomes for rolling the die, 1, 2, 3, 4, 5, 6, that is the sample space for that event. And the sample space is all of the possible outcomes that we have. Okay, so let's get into looking at how can we find what that sample space is. Right, now, again, sample space is all the possible outcomes. You flip a coin, you roll a 6-sided die. How many possible outcomes are there in the sample space? List the possible outcomes. Well, we want to stay organized with it, right? We don't want to jump around from, well, you could get a head and a 3. You could get a tail and a 6, right? You don't just want to jump around all over the place. Start with one of them, right? Flip a coin. I can get a head. I can get a tail. Right? Those are my 2 options for that. If I get ahead, well, I can get a 1, 2, 3, 4, 5, or a 6. So here are all those 6 possible outcomes that I could have if I flip ahead first and then roll a die. Same thing for tail. Right? There's going to be 6 possible outcomes here. So that would be my sample space. And there are 12 possible outcomes there. Now, how to tell without having to write them out? If they simply ask how many possible outcomes do you have in your sample space, what we have to do is think about whatever we are doing, and we're doing 2 actions here. How many different possibilities you have for each one. So you flip a coin, there are 2 possible outcomes, right? 6-sided die, there are 6 possible. If you multiply those 2 together, that's going to give you your total number of possible outcomes in your sample space. So there were 12, we get that by doing 2 times 6. So if I was going to roll 2 dice, that's a weird thing to say. It would be 6 times 6. There would be 36 possible outcomes for rolling those 2 dice. Now, you know, there are multiple outcomes that are going to look the same when you roll 2 dice, right? If you roll a 3 on the first one and a 4 on the second one, that's going to look the same to us as rolling a 4 and then a 3. But technically, these are different outcomes. Okay, so we got to keep that in mind. These are different outcomes. They both give us a 7 if we're going to talk about the sum, but they are different outcomes. A 3 first versus a 3 on the second one. That's different. Okay, so keep that in mind as we're going. What they're going to show you here, right? I wrote out the H1, H2, H3. They did what's called a tree diagram. You know, starting with the heads and the tails here, and then after a head, they're breaking it up into all 6. Tails breaking it up into all 6. This is beneficial if we're doing like 3 things. Let's say we were flipping a coin, rolling a dice, and then flipping another coin. Well, then after each one of these, you're going to have a head or a tail, right? And so you would see all the possibilities. You could have a tail, 6 tail, 6 head, right? You got to follow the branches of this tree to see all the different possible outcomes that we could have, right? So we would just be adding in another layer to that. And then you can see some questions are going to ask, well, how many different outcomes could we have where, you know, you have at least 1 tail and an even number, right? At least one tail and an even number. Well, this has an even number and at least one tail, so that one works, right? That possibility works. This one does not. This one does, right? So you could go through there and figure out how many of those outcomes fit the requirements of the question. Okay? So we're going to see a little bit of that. Now let's talk about probability in general, because this is, talking about sample space and outcomes and all that. When we talk about the actual probability of something happening, the probability that something occurs or that an event occurs or happens is the likelihood or chance that it will happen, that it will occur. Probability technically is from 0 to 1. Okay, so you would never say that there's a 100 possibility, right? You would say 100%, and we can say that percent because 100% is equal to 1. But it's technically between 0 and 1. And you can see we can list it as a fraction, as a decimal, or a percent. Any of those are fine. They all represent the same thing, right? 1/4, 0.25, 25% all represent the same thing. You see our range of possibilities here for probability. Starting at 0. 0 means it is impossible. It cannot happen. There's no way that it's possible that that's going to happen. Okay. Certain is a 1 or 100%. That is absolutely guaranteed to happen. Okay. So you just got to be careful saying a probability of 0 or 1, just because if there's even a remote possibility, even the tiniest bit of possibility, we can't say 0 or 1. Okay, it's got to be absolutely certain or absolutely impossible if we're going to say 0. Okay, in the middle, they use this phrase, equally likely to happen or not happen. Of course, we would call that a 50-50 chance typically, but anything bigger than the 0.5 is likely. Anything less than the 0.5 is unlikely. You get down here, it's very unlikely, right, before we get to impossible. When we're talking about that, typically we're talking about the theoretical probability of that happening. Okay, the theoretical probability is what should happen, right? The theoretical probability is what should happen. So we talk about theoretical probability, like the theoretical probability of flipping a head is 1/2 or 0.5. It's 50% chance. We know that. That's what should happen, right? The theoretical probability of drawing a red card out of a deck would be 1/2, right? Half of them are red, half of them are black. That's the theoretical probability, is that 1/2. Okay. We can find theoretical probability. It's the number of favorable outcomes, the ones that satisfy our requirements, right? What we're looking for, divided by the total number of outcomes. So if we're talking about rolling an even number on a die. Number of favorable outcomes, we got 2, 4, and 6. Those are the even ones. And then there are 6 possible. So 3 out of 6 would give us that 1/2. When we're looking for probability, it's written like this. This capital P stands for probability. And what's inside the parentheses is the event that we want to happen. So the probability, or P parentheses A, we would say that this is the probability of A occurring. And this is the probability of A occurring. Okay, so that's our theoretical probability. It's what should happen. Okay, what should happen. All right, so let's take a look at this problem, because you're going to see something like this in the homework. Okay. So the student taking a quiz randomly guesses the answers of 4 true and false questions. Don't do that. It's not good. But they do that. We want to figure out what's the probability of them guessing exactly 2 correct answers, not 2 or more, nothing like that. It's exactly 2. So we need to come up with the sample space. We need to come up with all the possibilities for that. And so this is where that tree comes into play. I'm going to use correct and incorrect. So C and I. Okay. Sure. I think that's what the book uses. That's why we're correct or incorrect. So that first true or false question, you can either get that correct or you could get it incorrect. right? Those are the only two options we have. So this is the first one. For the second one, again, we could get it correct or incorrect. Correct or incorrect. So regardless of what happened that first time, that second question is either correct or incorrect. It's going to be the same thing for the third and for the fourth. So we create that tree. Each one of these times that we branch off, it's either going to be correct or it's going to be incorrect. Sorry that you have to watch me just write letters on the board, but this is what we're doing. Okay, so there are all my possibilities. When I say all the possibilities, I'm talking every time you follow a branch down, that's a possibility. That's a new outcome, right? So each one of these at the very bottom represent a new possibility, represent a new outcome in our sample space. So like, for example, this C here, what that represents is I got it correct, correct, incorrect, correct. Right, so we follow the tree, follow the branches down to there, sort of like Plinko, right? You gotta follow that along down here, and that gives you what that possibility is. So they want the probability that the student guesses exactly two correct answers. So we want the branches where we only have two correct answers, not three, not four, not one, not zero, two correct answers, okay? So we have to look at each one of these and find which one's giving two. Well, this gives me 4. This is going to give me 3, right? Incorrect, but correct, correct, correct. This is going to give me 3. This one is going to give me 2. Okay, incorrect, incorrect, correct, correct. This one gives me 3. This gives me 2. Incorrect, correct, incorrect, correct. So 2 of them correct, 2 incorrect. This one gives me 2, right? That one gives me 0. So I got 3 so far. I got to check out over here. This one's going to work. This one's going to work. This one's going to work. And that's it. So I've got 3 here. I've got 3 here. So there are 6 total possibilities where it works, where I get exactly 2 correct answers. We got to know the total amount, though, the total number. That's if we count up all the way on the bottom. We're going to have 16. Or remember, that's 2 options here, 2 here, 2 here, 2 here. 2 times 2 times 2 times 2, or 2 to the 4th, gives me 16. We simplify the fraction. We know there is a 3/8 chance that we are going to get exactly 2 correct if we guess on this. There's a 37.5% chance that you're going to get an exact 50% on that 4-question quiz. Not great. Okay, but you're going to have to go through this process, and you're going to see a question on the homework that talks about choosing the correct door in a game show. You're either right or you're wrong. It's the same thing. Okay, it's going to be the same idea. You're either right or you're wrong. You've got your different days of options, and I think actually in the problem it's you win or you don't win, right? Win or lose. But it's that same idea right there. Okay? All right, moving on. Talking about the probability of a complement. The complement is the probability that something doesn't happen. Okay, so you see this bar over the A. That bar over the A means it's the complement of A. It's the probability of A not happening. It's sort of a negation, like we talked about earlier in the year. So if we were to talk about the probability of it snowing, okay, probability of it snowing, this would be the probability of it not snowing. The probability of it not snowing is 1 minus whatever the probability of it is snowing. Right? So if we say there's a 40% chance of snow, hopefully we're done with snow, but if there's a 40% chance of snow, that would look like this. The probability of it not snowing, right? That bar over it tells me the probability of it not snowing would then just be 1 minus that, or if it's a percent, 100 minus that. So the probability of it not snowing would just be 60%, right? It's got to add up to 100%. All right, moving on. So we talked about 36 different possibilities when you roll 2 die. This page, and this is page 670. 670, if you ever need to look up these 36 outcomes for the homework question or whatever, look at page 670. It shows it to you. Use that to count up your number or whatever. Right? If we want the sum that is not 6, right? That's the question A up there. We want the sum to not be 6. I would find how many equal 6. Find that probability, subtract it from 1. Right? The probability or the where the sum is 6, 5 out of those 36 give me a sum of 6. So if I do 1 minus that 536, I get 31 times it doesn't equal 6. And so that would be our probability that the sum is not 6. Okay, so you'll see questions like that. Again, if you need to look back, that's page 670 for those guys. But the next thing we got to talk about, and there's a lot in here, right? It's an intro, there's a lot of stuff. The next one we're talking about geometric probabilities. In geometric probabilities, use area. Okay, we're going to deal with area mostly here, but it could also be lengths or volumes. But we're going to deal with areas here. And so what this is going to look like is we're going to see something like this. Okay, we're going to see a geometric figure. And they're going to ask us the probability of something. So it might be, what's the probability that we land in the yellow? And we have to figure that out. Or it could be probably the basic one here is, what's the probability of scoring 10 points? Okay, because these are the number of points in this bullseye game or whatever we're doing here. So to be able to do that, we need to find the area. Okay, we got to find the area of where our event is happening, right? That's the event we want, is where it reaches 10. So we want to know where it reaches the 10, and that has to be divided by the entire area. Okay, so if we say that this is 3 inches right here, we can find the area of that. Remember, area of a circle, we haven't technically learned it yet, but area of a circle is pi r squared. So that would be pi times 3 squared would be where that event happens. And then we divide it by the entire thing. Well, if the entire thing, 3, 3, 3, this is 9 halfway. That means the whole thing is going to be 18. So the bottom would be the area of the big square, which would be 18 squared, or 18 times 18. So if I do that 3 squared times pi and I divide it by that 18 squared, that right there, that's going to give me the probability that the 10 is occurring, that we got the 10 points. Okay, is whatever 9 pi divided by 18 squared would be. And we would write that as a decimal, or we could write it as a percent, right? Probably not a fraction, because it's going to be a pretty big fraction with a long decimal on top. So that would be a decimal or a percentage right there. Okay. If they asked us instead what the probability of the yellow is, the probability of yellow is a little different, because now on top, we need to take into account that the yellow is only this ring. So we would be looking at the whole big, the outside of the yellow, which would be pi times 9 squared, right? Because the radius here is 9. But then we got to subtract what's inside the yellow. We got to look at that inner circle. And here, our radius is 6. So we're going to subtract out what's on the inside. We're going to subtract out that pi times 6 squared. Okay, so that's good. This right here is going to give me the area of just that yellow ring. Finding the area of the big circle minus the area of the smaller circle, that's going to give me the area of the yellow ring. Then again, I would divide it by the entire square to be able to get the probability that we're going to land inside the yellow. The area stuff can be a little tricky just because it's more, this is the most calculating that you're going to do here. Just pay attention to your area, okay? Think about it, do the best you can on it, okay? There are going to be other ones, but that's what we're looking at in terms of our example. All right, last thing we got to talk about here is a different type of probability, and this is our experimental probability. Experimental probability is what is happening, okay, or what has happened. So this would be different than theoretical, right? We talked about theoretical being I flip a coin, there's a 50% chance it's heads, 50% chance that it's tails. But our experimental probability would be I flipped a coin 10 times, this is what happened. So my theoretical my experimental probability of getting ahead might not be 50, right? Or 50%. It might be 7 out of 10 because that's what actually happened when I flipped that coin 10 times. So our experimental is not necessarily going to be that theoretical. Theoretical is what should happen. Experimental is what did happen, okay? And so what they're going to do for your experimental probabilities is they're going to show you the result of some experiments. They're going to say, we did this 20 times. Here's the result. What was the experimental probability of getting a 6? What was the experimental probability of doing the spinner and landing on green when it happened 4 times out of the 25 we did? Okay. So experimental, theoretical are 2 different things here. Experimental is what has happened. You see it here. It's the number of successes over the number of trials. So the number of times it actually happened over the number of times we tried to get it to happen. That's our experimental. Okay, so if we look at this problem, there we've got our spinner, blue, yellow, red, green, all even amounts. Okay, and then we have these results where we spun it 20 times. This is what actually happened. So we know our theoretical probability is every one of those has a 25% chance of landing.
Jolene from GRBC, please come to the main office. Jolene from GRBC, please come to the main office.
Our experimental probability, since we spun it 20 times, our experimental probability of yellow is 3 out of 20. 3 out of 20, 9 out of 20, 5 out of 20. We want to simplify that down to 1/4. So they're asking for which color is the experimental probability the same as the theoretical? Well, we know we have a 25% chance of landing on each one of those colors. So 25% chance that 1/4 red is the one that matches up. Okay. We just got to know the difference between the experimental and the theoretical. Okay. Just keep those straight in your mind. Theoretical, what should happen, experimental, what actually did happen when we did our experiments. Okay. That's what we're looking at in terms of our probability here. You know, you might see some graphs. It's the same idea, right? This is experimental because it's how many of these actually happen. This is the result of the survey. Okay. What's the probability that a pet owning adult chosen at random has a dog? Well, you got to add all these up to get the total, and then we can do the dog divided by the total. That's our experimental probability there that is going to happen. Okay. All right. So a lot of stuff here on the intro section of probability. We don't get too far into probability. This is really the extent of it. We'll go a little bit further in the next couple sections. But knowing the difference between experimental and theoretical is huge. Being able to find that area probability, okay, that geometric probability using the area, that's going to be big too. So make sure that we can do that. Okay. And that should be it for section 12.1.